In these short ghost lectures, we finish off the matrix perturbation results that we've been building up towards. So first, let me remind you some of the basic results that we've developed and the ones that we'll need. So the first one, which is very simple but foundational, is says the following thing. Let's let X be a matrix with independent columns. And now I'm thinking about X being a matrix that looks like this. R of X, as usual, will always denote its range. And I'll let let's let script X be this subspace. The question is, when is this an A invariant subspace? So the theorem says that X is A invariant if and only if y a x equals 0, where y is a matrix that whose columns span the perpendicular space. So the columns of y span the perpendicular space to x. So let's see why this is the case. It's quite straightforward. So what does x being A invariant mean? X is A invariant. This is the same as writing that A times x, meaning A times any vector from the subspace, again lands in X. And this is the same as writing that A times X is perpendicular to perpendicular space to X. These are equivalent. This in turn is equivalent to saying that the range of A times now the matrix X is perpendicular to the range of Y. So again, why is that true? Because the range of AX is exactly equal to A times every vector in the subspace X. And similarly, the range of Y is every vector in the perpendicular space of Y. And then this is equivalent to the statement of the theorem, which is Y times AX is equal to 0. Now, an immediate consequence of this is the following. So suppose X is A invariant, and let's let X1 be an orthonormal basis for this A invariant space X. And let's complete it to be an orthonormal basis for the entire space by Y. So in other words, let's let X1 and Y2 be unitary. So columns of the joint matrix X1, Y2 are an orthonormal basis for the entire space. In that case, basically the theorem that we said above says that X1, Y2 Hermitian transpose times A times X1, Y2 has this particular form. L1, 0, L2, or H is just some matrix. So X will not, in particular, will not always be 0. So that's one consequence, and the other one, which is just comes from multiplying this out, is that AX1 equals X1 L1. And if you'll remember, this means that L1 is a representation of the matrix A on the space X with respect to the basis given by the columns of x1. The second definition we saw, so I should mention that all of this is review from last time. The second definition is that of a simple invariant subspace. So X is a simple invariant subspace if, first of all, it's invariant, and again, I mean, this is all in reference to some matrix, some linear operator, and if the spectrum of L1 and the spectrum of L2 are disjoint. So again, by this notation, I mean the eigenvalues of L1. So this motivated the following definition of an operator that is going to be extremely useful for us when we talk about our matrix perturbation theorems. And it's essentially going to be a way for us to measure the distance between L1 and L2. So given two matrices, A and B, and then for us, we will be using L1 and L2, but I'll just give the definition in terms of A and B. We can define the operator T of AB that takes a matrix X and returns AX minus XB. And one of the main things that we proved last time was that T is non-singular if and only if the spectrum of A and the spectrum of B are disjoint. And we proved one direction in class last time. In class, we proved one direction. And the second thing we showed, which was a quick corollary, was that the actual spectrum of T is equal to, and this to the spectrum of A minus the spectrum of B, and by this I mean element-wise. In other words, the L of A is a set, L of B is a set, so L of A minus L of B is a set which is the difference of anything in A with anything in B, so there are more elements. So one thing that I left as an exercise, we discussed this last time, is just to check that that T is a linear operator. And some people were asking about whether we can represent T as multiplication by a matrix, and you can, but it takes a little bit of thought of how you would do this. So the point is that that any linear operator in finite dimensions, which is what we have now, can be represented as multiplication by a matrix. And left multiplication. So left multiplication by a matrix. So check how that would be done. Okay, so since we're on this thread, we'll just take a brief detour and mention another important quantity, and that's this notion of spectral resolution. Of a matrix. So the following result comes out of the definition of a matrix of a subspace being simple and invariant. And it says the following, that if X is invariant, A invariant, and simple, then in fact its complementary, its orthogonal complement is also invariant. And you can check that this doesn't always have to be the case. So let me just leave this as an exercise. Find an example of an invariant subspace X where its perpendicular subspace is not invariant. And you don't have to look too far to find something like this. Just think about the main assumption in this theorem, namely simplicity. So if you take something that's not simple, then this is not a necessary and sufficient condition, but for this exercise, that's how you should think about it. So what is it? So what's a consequence of this? So in particular, this means that there exists a similarity transformation which may not be unitary, such that x1, x2 inverse times A times x1, x2 is equal to L1, L2. So now we've replaced that H with a 0. So this is the previously we had H here, but now that's 0. And another thing to notice is that we've kept x1. So this is basically means that I've managed to extend the basis already given. And a definition here is that so you can check that A, we can always write further consequence is that we don't have to, is that x2 isn't just arbitrary, that we can do this in the following way. So let me write this out a little more carefully. So if we start out with so in particular there exists an x2 and a y1 such that x1, x2 inverse is equal to y1, y2. So recall that we had started out with an x1 and its completion to a basis for the entire space by y2. And so now this theorem says that there exists a y1 and an x2. And this is what's called the spectral resolution. So for this choice of x1, x2, y1, y2, we can write that A is equal to x1, L1, y1 transpose plus x2, L2, y2 transpose. So note that essentially this statement and this statement, these things together are equivalent to this statement here above. Let's let P1 equal to x1, y1 transpose, and P2 equal to x2, y2 transpose. So again, let's think about what is x1 and x2, x1 and y1. Basically, the xi and the yi play the role of left and write eigenvectors. They may not be eigenvectors themselves because we don't know that we can decompose the space into one-dimensional invariant subspaces, but they play precisely the same role. So one thing that you should check, maybe I'll write this as an exercise, is what happens in the one-dimensional case. In other words, check what happens, and what I mean by what happens is what's x1, what's y, what's x2, what's y1, what's y2, etc. When x is a simple, invariant, and one-dimensional subspace. Okay, so back to P. Something else that you should check about P, which is pretty straightforward, is the following: that P looks like a projection operator. So Pi times itself is equal to Pi. So by I just mean I equals 1, 2. Also, P1, P2 is equal to P2, P1, and that's equal to 0, of course. And third, that we can decompose A as P1, A, P2 plus P2, A. Oops. P1, A, P1, P2, A, P2. And P1 is called the spectral projection of x1, and something that we'll explore in the homeworks is the following. So we will see in a problem set exercise, in a future problem set exercise, that the magnitude of P1 controls the sensitivity of eigenvalues in L. And we'll see this by looking at the one-dimensional setting.